All right, guys, so today we are covering the last chapter that we're going to cover in Algebra 2. Chapter 6. All the way up to the final. So, exponentials and logarithmic functions. This is the last thing we're going to be covering in Algebra 2. Exponentials and logarithmic functions. Now, when we talk about exponentials, exponential function is just a function that increases more and more as it continues along the x-axis. Now, most of the ones that we've covered have a kind of steady increase as they go. Now, a type of exponential function we can consider is 2 to the x. 2 to the x would be an exponential function, because if we think of it with the x and y values, when x is 0, if we plug this in for 2 to the x, the output would be 1. If we plugged 1 into 2 to the x, we get 2. So we can see that the y values increase by 1. Now if we say when x is 2, the y value is now 4. So it increased by 1, now 2. And when x is 3, it is now 8. 4 is 16. 5 is 32, and we keep increasing by a rate of 2 each time. And this here is not too bad. Now, if we said 5x, 5 to the x, it would increase even faster. And we can look at this as a graph, 5 to the x. And if we looked at the tables, well, that when x is 0, the y value is indeed 1. When x is 1, it's 5. When x is 2, it's 25. Then 125, 625, 3,125. We can see that the y values keep increasing faster and faster as it goes up. That is why we call it an exponential function, because the amount of change increases more and more as the x values increase. E tells us that it's times 10 to the 6th. So that means it has 7 digits, so 390,000. So that means when x is 9, it's gone over 1 million. So we haven't even got to 10, x value of 10 for x to the 5th, and we have over 1 million. So these will increase faster. Now there's 2 types of exponentials that we can talk about. The first one is called exponential growth. That means as the x values increase from left to right, as we increase the x values, the y values are going to increase. So the parent function, f of x equals b to the x, where b is greater than 1, is the parent function for the family of exponential growth functions with base b. The graph shows the general shape of an exponential function. So if b is greater than 1, it's considered an exponential growth. Now, the domain of b to the x is all real numbers. So we can plug any x value in to an exponential growth. And the range for the base, just b to the x, is y is greater than 0. Any questions on this here? Now, the other one we have is exponential decay. Now, a function is considered exponential decay if the base is between 0 and 1. So if the base is between 0 and 1, it's considered exponential decay. And it's decreasing. Now we don't consider anything less than 0. We don't consider a negative base, because that one, they behave differently. They behave weirdly for the most part. Because if we said here, well, we can clear that out. So if I said negative 2 to the x, and we graph, well, before we graph that, so I'm going to hit enter and look at, say, 5 to the x first, we have this here. So that's the graph of 5 to the x. Now, I'm going to turn this one back on and say graph. And so if we look at this here, do we have a blue graph? No, but we do have values. Now, if we look at the table for the blue values, well, at -1, it's negative 0.5. At 0, it's at positive 1. At 1, it's at negative 2. At 2, it's at 4. So if we see here, it's jumping between positive and negative values. And because it does this jump from one to the other, it's not really a function. We do have an equation for it, but it's not a function because it's doing this positive negative jump back and forth. We don't have a nice smooth line for it. So that's part of the reason we don't talk about values of b, values of this base that are negative. So we ready for this difficult example problem? Tell whether each function represents exponential growth or exponential decay. We're not going to graph it, but then we're going to evaluate when x is 2. So we look at the first one, y equals 2 to the x. Would this be exponential growth or exponential decay? And the reason we would say this is growth is because the base is greater than 1. Now we want to evaluate it when x is 2. We're replacing x with 2. So we have 2 to the second power. And 2 squared is 4. Yes. Any questions on any of this here? Let's look at part B. Y equals 1/2 to the x. Would this be exponential growth or exponential decay? Decay. Because our base is between 0 and 1. Now we want to evaluate it when x is 2. So we say y is equal to 1/2 to the second power. Parentheses squared. And we can plug it into the calculator, and 1/2 to the second power is 1/4. Questions on this here? Let's look at the next one, part A. Y equals 1.3. So the first thing we need to determine if it's exponential growth or exponential decay. Growth, even though it has a decimal? Yeah. Even though it does have a decimal, it is still greater than 1. Now we need to evaluate it when x is 2. So we have y equals 1.3 to the second power. Now we could do it by hand. We can do 1.3 times 1.3 and work it out. Or we can say 1.3 squared is 1.69. Questions on this here? Any questions on anything we've done so far? Let's look at the last one on this page. Y equals 1/3 to the x would be decay, because our base is between 0 and 1. And if we evaluate this when x is 2, we would get 1/9. Because 1/3 times 1/3 would be 1/9. Luckily, that one there is not too bad to calculate. Any questions on any of this here so far? Be ready for the next two. So these here, determine whether the function represents growth or decay. We're not asked to evaluate anything, we're just asking for growth or decay. So number one would be because the base is greater than 1. 2, decay, We have a fraction, and that fraction is between 0 and 1. Number 3, decay, because 0.25 is between 0 and 1. And lastly, 1.5. Yes. Questions on any of this here? We feel comfortable with this here?
Yes, sir.
Yes, please. The natural base E. Yes. We have this here. The history of mathematics is marked by the discovery of special numbers such as pi and I. We know pi is an irrational number and I is imaginary. Another number is denoted by the letter E. The number is called the natural base E, and this really comes in with logarithms. Now, this E is expressed by the expression 1 plus 1 over x to the x as E approaches E. So that there approaches E as x increases. So what they're saying is if we take this for 1, so 1 plus, now so if we did it with 1, we'd have 1 plus 1 over 1 to the 1. Well, this is just going to be 2. And we take that value of 1 plus 1 over 2 to the second and add to it 1 plus 1 over 3 to the third, and keep adding all these values together to get what E is. And this here will end up approaching this number here. It'll get closer and closer to it. Now, just like with pi, we can't actually get the full value of pi. It's a decimal that is a non-repeating, non-terminating decimal, but we can get closer to it. Now, we can also do stuff with E. Now, E we can treat just like with pi, or I we can do a lot of stuff that we can do with variables, but it does have a special value. So if we multiplied, say, e to the third times e to the sixth, when we multiply like bases, we do what? We add the exponents. So 3 plus 6 is 9. So this is the same as if we said x to the third times x to the sixth. Multiply like bases, we add the exponents. If we divide like bases, here 16 divided by 4 is, well, e to the fifth over e to the fourth. If we divide like bases, we subtract the exponents. So 5 minus 4 is 4e. We could say 4e to the first or 4e. In the calculator, whenever you type e in, you have to give it an exponent. So even if one's not written, we do have to put it in as 1. The calculator needs an exponent for e, even if it is 1. Since we only have one term, we're multiplying this by itself, so we can apply the square to both terms. So we'd have 3 squared, which is 9. B. Powers of powers multiply, so we'll multiply the negative 4x by 2. Negative 4 times 2 is negative 8x. Questions on how we got 9e to the negative 8x? Now I did put another set of equals because we can't let e have a negative exponent. So to make it positive, we move it from the numerator to the denominator. Any questions on A, B, or C? We good with A, B, and C? Let's look at 1, 2, 3. E to the 7th times e to the 4th would be what? E to the 11. Because we can do 4 plus 7. Powers of powers multiply. When we multiply like bases, we add. 24 divided by 8 is 3. E to the third. Because when we divide like bases, we subtract the exponents. So 8 minus 5 is 3. Since it's bigger on top, it stays on top. And lastly, we can apply the power to 3 to both terms. So 10 to the third is 1,000. E. So negative 3x and 3 would multiply. Powers of powers multiply. Which would give.
I'm stupid. I did 10
10
times.
to the third.
Oh, did you do that too? Yeah, it's like that's 30. What are you talking about? I know. I forgot about the next one.
And to make the exponent positive, we would move it from the numerator to denominator. So 3x times 3. Powers of powers multiply. Because we have the power. Yes. Because when we have a power, so the negative 3x to the third, we multiply those together. Because we're saying that we have 3 of them. So 3x plus 3, or 3x to 3x and 3x. 3x and 3x is 6x. Another 3x would make it 9x. So we multiply. Questions on any of this here? Now, E, guys,
Bring it back in.
with E, the natural base function, a function of the form y equals a times e to the rx. So just like our exponential growth and decay, we can have this with E. Now, when a is greater than 0 and r is greater than 0, the function is exponential growth. So when the number in front of E is greater than 0 and the number in the exponent is greater than 0, it's exponential growth. Now, when the number in front of E is positive and the number in the exponent is less than 0, it's exponential decay. Now, notice with this here, the number in the exponent for growth is greater than 0. So it means that value is positive. It's not talking about a whole number or a decimal. It's saying it's positive. It's greater than 0. And it's exponential decay when that number in the exponent is negative. It's less than 0. So even though we could have a number in the exponent that's 1/2, if it's positive 1/2, it's still growth. If it's positive 5, it's still growth. However, if it's negative, it's going to be decay. And there's a reason for that, because again, we said E was approximately 2.718. So that is a number greater than 1, yes? So by definition, if the exponent's positive, the base is indeed greater than 1. Now if we said E was to the negative x, and they gave us an example of it here, well, how do we make the exponent positive? We move it from the numerator to the denominator, which is telling us that we have 1 over e to the x. Now, according to our exponent properties, we can move the x to apply it to the whole thing. And part of the reason this does work is the fact that 1 to the x is just 1. It doesn't really change anything. So we have really saying that if the exponent's negative, we have 1 over e to the x. We have 1 over 2.718. This is now between 0 and 1. It would be a decay function because the base is now between 0 and 1. But we don't have to rewrite it as this here, because if the exponent's negative, it is decay. If the exponent's positive, it's growth. And this only applies to E. So if we look at this here, A, 3e to the x, would this be growth or decay? Growth, because the exponent is positive. B, decay, because the exponent is negative. Any questions on A or B? How about number 4?
That's decay.
So why did we say A was growth? The exponent's positive, so 4 would be.
What about the first thing we learned?
So,
Is that just wrong way
no, it works if the base is a number, because here the base is E.
Oh, so our base is E now, so we're looking at the next one.
Yes.
So then the next one's decay.
Mm-hmm.
I thought we got to throw away the first thing.
And it still holds true. It's just if the exponent, because the first one we talked about, if the exponent's greater than 1, it's growth. If the exponent's between 0 and 1, it is decay. And we're talking about a number itself. With E, if the exponent's positive, it's growth. If the exponent's negative, it is decay.
What if you have
Positive and negative?
yeah, no, like negative 1/2 to the third to the negative fifth.
This here?
No. Hold on, let me write it down.
Sorry, she's new.
Sorry, gotta think about it. Like this.
Like if we combine the first thing that we
And
learned in
then
the
you put E beside it with the no, fuck this. Like,
well, it's like yeah.
Guys, you can't tell her that.
she doesn't understand.
Like this here?
I think so.
Or something where we have one of each.
Yeah, one of
Yeah.
So let's clear both of these out and let's see. So we have 1/2 to the x times e to the negative x. Well, that would be, because this here would be decay, because both of them are decay. So this here is growth. Because even though 1/2 is a decay function, e to the x is a growth, they're opposites, it works out that the growth of e to the x is bigger than what the 1/2 is decaying at, so it takes over.
Oh.
Now, I did, instead of 5, I just did this here. Now, they are both to the x, yes? Well, since they're both to the x, we can treat it the same as 1/2 times e to the x. Because if I have two things to the same exponent, we can write it as 1 for that exponent, which is the same as e over 2 to the x.
Oh.
Well, e is 2.71 going on. So this here, this base is still greater than 1, so it is growth. Now, some of it ends up looking at the base. Now, because the base of e is a number greater than 2, 2.7, we look more at the exponent because that base is set. With the other one, since a number, the base is not set to that single number, it varies, we look at the base.
Oh, that's the
All right, thank you.
I'm going to give you 4 here.